Hello, everybody, and welcome back to another lecture in Geography 340, Climatology. I am Dr. Zach Hilgendorf. Today, we're going to be talking about the El Niño-Southern Oscillation and the Pacific Decadal Oscillation. These are kind of putting together what we've been talking about for these last few weeks, looking at global scale trends in pressure, temperature, and currents and gyres. So kind of a big mesh of all the stuff we've been talking about over the last little bit. So starting off, some quick definitions. We have anomaly, simply A equals without, nomos equals law. These are basically maps that show the difference from normal conditions. So we've talked about temperature anomalies and pressure anomalies before. We've got the SST, or sea surface temperature. These maps are useful for identifying unusually warm or cool water. This is important because that's kind of what we're identifying when we're talking about ENSO and PDO phases. So a positive sea surface temperature anomaly equals warmer waters than normal. Vice versa, negative SST equals cooler waters than normal. The El Niño-Southern Oscillation, or ENSO, is basically in reference to the child, is the way to put it, and for a good reason, because when this was originally observed and originally kind of commented on, it was always around Christmas time, and it was observed as a warm surface current in equatorial eastern Pacific that occurred periodically. So think of Latin America, where this was being primarily observed. Typically, the dominant religion is Catholicism or Christianity. El Niño, meaning kind of the child or the babe, in reference to the newborn Jesus at this point. The Southern Oscillation is equal to a change in atmospheric pressure over the Pacific Ocean, accompanying the El Niño. Now, these weren't always linked together. This came about in kind of increments, as we'll see here in just a slide or two. And so describes a combined oceanic atmospheric disturbance. So what is the ENSO cycle? It's a naturally occurring phenomena. It's where the equatorial Pacific fluctuates between warmer than average El Nino and colder than average La Nina conditions. Changes in sea surface temperatures affect the distribution of tropical rainfall and atmospheric circulation features. This is what we refer to as the Southern Oscillation. And changes in intensity and position of jet streams and storm activities occur at the higher latitudes. This is how this effect ripples out on more of a global scale. So the history of the El Niño Southern Oscillation got its start and was really documented all the way back in the 1500s. This term was used to describe the annual appearance of warmer waters along the coast of northern Peru around Christmas time. As we mentioned, it was northern Peru and Ecuador is where we kind of first observed these trends. In some years, the warm waters appeared earlier and lasted longer, and eventually the term El Niño was applied to periods of anomalous warming. The stronger events actually disrupted and were observed to disrupt local fish and bird populations. So this was kind of a way that the people of the time noticed some of these trends occurring, was based on where these species were distributed and migrating from time to time. And because I have to, at least once during this presentation, El Nino obviously is there's a very famous Chris Farley skit from Saturday Night Live in the 1990s. Where Farley was playing El Nino, or as he refers to it, it's Spanish for the Nino. This has been well integrated into our culture and into our history as peoples in this part of the world. The Southern Oscillation, beginning in the late 1800s, scientists began to describe these large-scale pressure fluctuations. Sir Gilbert Walker and some colleagues extended the early studies and determined that a global scale pressure fluctuation, which they deemed the Southern Oscillation, is related to rainfall anomalies in many areas of the tropics, such as India and South America. Southern Oscillation was used as the basis for rainfall predictions all the way through the 1930s. So the discovery of this El Nino Southern Oscillation, they were studied as separate phenomena, as I mentioned previously, until the 1950s and 60s. Important works by Berlage, 1956, and Björknes in the late 1960s demonstrated a link between the two phenomena. Studies at the time showed that anomalous warming of waters during El Nino phases extended over a large portion of the equatorial Pacific. And you can kind of see here just an example of ocean temperature departures for kind of a stronger El Nino phase, 3.4 here, where we see kind of increases. The warmer would be El Nino, the colder, the blue would be La Nina. So it's important to think of this ENSO cycle as a coupled oceanic atmospheric system. So in that system, the atmosphere drives the ocean and the ocean drives the atmosphere. It's what we call a positive feedback loop between the ocean and the atmosphere. So an example would be, we have weaker equatorial trade winds. We have colder water upwelling in the east that will decrease. We have surface warming of the ocean because of that, those shifts. We see a reduction in the east-west temperature gradient, and we see weaker equatorial trade winds. So what we're seeing here is kind of a weakening or changing of the system as a whole that's feeding off of itself. So what does that look like? Well, in an average year, so if there was a neutral phase, a neutral ENSO phase, we would see this kind of setup here where you've got your Walker circulation patterns. For example, we see New Guinea, South America. We see cool lower water. We see that thermocline, so that gradient of temperature within the water column. So the warmer water is kind of sitting over the western portions there. Cycling back, we see upwelling along the coast of South America. The trade winds are pushing some of that water as well. These kind of think of these big gyres that we talked about in the last lectures. So we've got this kind of circulating trend here. So here, winds and sea surface temperatures are coupled. Sea surface temperatures influence the winds and vice versa. The easterly trade winds help push warm waters to the western Pacific and upwell cold water along the equator and the eastern Pacific. And then warm water heats the atmosphere, the air rises, as warm air does, and low-level trade winds converge with the warm water. Subsiding air occurs in the eastern Pacific basin. And we can see kind of a three-dimensional or slightly oblique diagram at the bottom right there, looking at just this phenomena. This is a neutral phase. So we can see almost perfectly that kind of thermocline right there with the upwelling, warm water kind of on top, the cold air or cold water in the deep. Coastal winds are kind of driving north along the coast of Ecuador and Peru. And then we see that Walker cell circulation of kind of warmer air and larger storms over kind of the South Pacific and off the coast of Australia and New Guinea. And then that is circulating to those colder air parcels, which are off the coast of South America and Latin America. In an El Nino, we see a weakening of our easterly trade winds. That thermocline deepens and cold water upwelling decreases in the eastern Pacific. We can see that kind of a flattening in that bottom right graph there. And then convection shifts eastward over the central and or eastern Pacific Ocean. Convection becomes suppressed over the far western Pacific and Indonesia. So we kind of see those clouds have shifted, bringing greater quantities of precipitation over the east coast of South America and Central America. Note, the location of the warmest sea surface temperatures greater than 28 degrees Celsius determine where that tropical convection is going to be located. So what does this look like from a pressure sense or a surface pressure sense? Here we can see with El Niños, we have a weak Aleutian high. We remember back to our pressure lecture from a few weeks ago. Here is kind of that high pressure system that sets up often in the winter is kind of suppressed because of this weakened gradient. The polar jet stream is kind of shifted a little bit to the north. We have warmer air along the coast of Alaska, British Columbia, Washington. We see wetter conditions in the Pacific or in the U.S. Southwest, cooler air along the Gulf Coast or in kind of the northern portion of the Gulf Coast, and almost a dry pocket over areas like Illinois, Indiana, Ohio. In severe El Niños, we can see kind of the effects on a global perspective. We see drought throughout Africa and India and the Central America, the West Coast, or sorry, the East Coast of South America, throughout Indonesia and the South Pacific. We see severe coastal erosion along California, Washington, Oregon, British Columbia. This is something that's pretty typical, pretty well observed. We see tropical storms forming and impacting areas like Hawaii. We see coral reef damage along the Galapagos. We can see kind of just to get a general sense of how severe El Niños can really impact and negatively alter a lot of these regions, these coastal regions and shallow ocean regions. We can see here impacts are generally more extensive during the northern winter is where we see this primarily taking effect. So warm episode relations, so this is December through February. In India, China, it's warmer. Along Madagascar, the south portions of Africa, into kind of, again, Indonesia and the islands south of China. That's drier and warmer. We see a lot of drying kind of in those equatorial or subequatorial regions throughout the middle of the Pacific. Wetter conditions along the southwest US, wetter and colder conditions along the Gulf Coast, wetter and warmer conditions right along the equator, near between kind of Papua New Guinea and Ecuador and Peru. In June through August, if that trend is holding consistent, we typically see this as drier conditions in India throughout most of Pacific Islands, into Australia and New Zealand, wetter conditions in kind of the Central Pacific and up through Oregon, drier and warmer in the Caribbean, much warmer along the west coast and east coast of South America, and a bit wetter in some other spots. So typical global El Nino impacts in Indonesia, we see for the entire duration of an El Nino event, drier. Same with Northeast Brazil in March through May, in Central America and Mexico, May through October, and Southeast Africa from December through February. Along the West Coast and in South America through March and May, we typically see wetter conditions. And in Central South America, we also see wetter conditions through June and December. From in perspective of anomalous precipitation, so millimeters per day, during strong El Nino episodes, so rainfall departures as large as plus or minus 8 millimeters per day or 30 inches in a season result in changes in the patterns of tropical heating and changes in the position and intensification of mid-latitude jet streams and planetary waves. So here we can see in January through March, of 1983 and January through March of 1998, two particularly strong El Nino years. We see kind of intensification on both perspectives. So in kind of the subequatorial regions north of Australia, we see intense kind of drying. Likewise, you see intense wetting kind of along the north tip of Australia all the way across through the South Pacific Islands, all the way to the west coast of South America. In moderate conditions, you see slightly dampened examples of just that. Rainfall departures are less during weak and moderate warm episodes. Smaller changes occur in the pattern of tropical heating and in mid-latitude jet streams and planetary waves. For La Nina events, we see a strengthening of our easterly trades. We see greater convection near New Guinea, stronger storms. The Walker circulation is enhanced, stronger upwelling of cold ocean currents. That cold becomes more shallow, so it kind of increases or decreases in depth below the surface of the ocean. That thermocline kind of steepens a bit more. The warm water is pushed further off the coast. And then what does that look like from a pressure perspective? We have a strong Aleutian high. So our jet stream we can see is dipping much further to the south. Think of when we have some of these really, really strong and cold years, that descending air coming down from the polar regions being brought down by our polar jet stream and this variable Pacific jet stream here. So we have this blocking high pressure system that kind of dominates most of the region to the west of North America. We see drier conditions in the portions of the Southwest through Florida, warmer as well, wetter south of the Great Lakes, so Indiana, Ohio, Kentucky, and Tennessee. Wetter conditions along the coast of South British Columbia, so Victoria, Vancouver, through Washington, Oregon, and Northern California. Global impacts for La Niñas include mid-latitude impacts generally occur during the winter season. So in the Northern Hemisphere through December, January, February. In the Southern Hemisphere, June, July, and August. During cold episode relationships, so December through February, we see cooler temperatures along the west coast of Africa, wet and cool along the southeast coast. We see this kind of wetter wedge kind of replacing where it was dry and warm through the north portion of Australia, south of China, which the dry and cool replaces what was previously wet and warm. We see drier conditions, as we said, in the south of the US, north of Mexico. And then if you look from June through August, we see similar trends hanging out in Western Africa. It is wetter and colder in India, South China, through much of the regions down there, Indonesia, and the islands throughout. Warmer conditions and some wetter conditions throughout Australia, New Zealand, Papua New Guinea. Drier conditions in kind of the central portion of the Pacific. Colder and wetter conditions in the northern portions of South America, portions of Central America, the Caribbean. Colder conditions along the coast because that upwelling from colder currents and the increase in the thermocline is kind of chilling down the west coast of South America. And then drier conditions along that eastern edge. So typical global La Nina impacts in Indonesia, North Brazil, Central America, Mexico, and Southeast Africa. We have wetter conditions through variable portions of the year. Along the west coast, South America, and Central South America, we see drier conditions prevail. Anomalous precipitation in millimeters per day. during La Nina episodes. So rainfall departures as large as plus or minus 8 millimeters per day result as well. We can see here kind of flip-flops, what you'd expect when we saw our El Nino versus our La Nina phases. So here, El Nino recurrence intervals. So the El Nino is kind of or these ENSO phases set up on a quasi-regular time span. We can see here, this is a figure from the National Oceanic and Atmospheric Administration. So these El Ninos or these ENSO events kind of cycle roughly every 2 to 12 years. The Pacific has alternated between El Nino and La Nina events since the 1950s, and we can see here. Currently, we are in as of recording this, so November of 2022, we are in a La Nina phase, a pretty decently strong one that we can see here. So comparing El Nino and La Nina phases. So what do we see in the tropical Pacific? We see changes and differences in sea surface temperatures, precipitation, sea level pressure, the southern oscillation, so high versus low phases, and low level winds and thermocline depth. We've already kind of talked about each of these and separately looking at the El Nino and La Nina phases in those previous slides. So here we can see the equatorial cold tongue is weaker than average or absent during El Nino phases, resulting in positive sea surface temperature anomalies, warmer temperatures. The equatorial cold tongue is stronger than average during the La Nina, resulting in negative sea surface temperature anomalies. So what does that look like? Well, you see the green circle there. What we're basically looking at is kind of temperature in degrees Celsius, and look how prevalent that warmer water is from kind of the South Pacific all the way through, the Indian Ocean, South Pacific, all the way through to the coast of South America, whereas that disappears during La Nina phases. From a precipitation perspective, we see enhanced rainfall occurring over warmer than average waters during El Nino phases, and we see reduced rainfall occurring over colder than average waters during La Nina phases. From a temperature perspective, we have positive sea level pressure anomalies over the western tropical Pacific, Indonesia, and Australia, negative sea level pressure anomalies over the eastern tropical Pacific, middle and high latitudes over the North Pacific, and over the US. The opposite pattern prevails for La Nina phases. This pressure seesaw between the east and west is known as the Southern Oscillation. Looking at low-level winds and thermocline depth, just to kind of put these side by side, we've already looked at these before. During La Nina events, we have stronger than average easterlies lead to a deeper, shallower than average thermocline in the western Pacific. In El Ninos, we see weaker than average easterlies leading to a deeper or shallower than average thermocline in the eastern equatorial Pacific. And then looking at upper jet stream differences during La Nina phases, we see kind of that variable Pacific jet stream, this deep plunging meander of the polar jet stream, and drier prevalent conditions throughout much of the South United States and northern Mexico. During El Nino phases, we see kind of a weaker north shifted polar jet stream because the Pacific jet stream is kind of amplified and really driving storms and circulation across the region. So we see wetter conditions throughout much of the South United States and northern Mexico. And then another one, we have our Pacific Decadal Oscillation. We're just going to spend a few slides talking about PDO. So Pacific Decadal Oscillation is a long-term ocean fluctuation of the Pacific Ocean. It is described often as a long-lived El Nino-like pattern of Pacific climatic variability, waxing and waning every 20 to 30 years. So think of the El Nino every 2 to 12 years. The PDO is every 20 to 30 years. So from ocean surface topography data together with ocean and atmospheric data, we can determine whether we are in a cool phase or a warm phase. Cool phase is characterized by a cool wedge of lower than normal sea surface heights and ocean temperatures in the eastern equatorial Pacific, and a warm horseshoe pattern of higher than normal sea surface heights connecting the north, west, and southern Pacific. In warm or positive phases, the western Pacific Ocean becomes cool and the wedge in the east warms. So what we typically see, or how that impacts climate and weather trends, see more frequent and stronger El Nino events occur during periods dominated by the warm or positive phase. See more frequent and stronger La Nina events that occur during periods dominated by the cool phase. In 2014, we apparently flipped from cool to warm, although we're kind of seeing that now. So here we can kind of see what this looks like. So this is PDO index from the National Oceanic and Atmospheric Administration, the National Climate Environmental Indices. So the change in location of cold and warm water masses alters the path of the jet stream. So put simply, the jet stream in the northern hemisphere delivers storms across the US. The PDO phase that we appear to have entered will act to steer the jet stream further north over the western United States. So here you can see, even though we apparently flipped, I think we flipped again. It looks like we are in kind of a colder phase. We are in a prevalent La Nina phase right now. So it kind of matches up. So we see these cool phases kind of alternating 1890 to 1924, 1947 to 1976, 1998 to 2013. See these warm phases in 1925 to 46, 77 to 98. We see another little one from 2014 and maybe 2016, and now we flipped back to a cold phase or a negative phase where we see negative sea surface temperatures in the last couple of years. So just a brief recap, we talked about the El Niño-Southern Oscillation, including El Nino and La Nina events and phases. We talked about the Pacific Decadal Oscillation. So this kind of brings together much of what we've been talking about over the last number of lectures, looking at sea level pressure or pressure distribution, upper atmospheric trends in circulation, ocean circulation, and temperatures. So hopefully this puts it into perspective and you kind of understand a bit better of what we're talking about when we say El Nino or La Nina phases, especially because of the impact they have on climates. We didn't really dive into it here, but we will a little bit later on in the semester when we talk about the anthropogenic impacts that we're seeing, kind of anthropogenic global warming and climate change, the impacts that we are having on these ENSO events, and they are there. So we'll save that for another day. Some great papers to read that I will provide to you then. But until then, we will see you in the next video. Thanks.